So how many people are really, really excited for me to talk about AI? Yay! You will be disappointed. Because, I mean, frankly, this is the thing, right? Every time I go to a conference, every time somebody asks me to do a keynote, there's always this question, like, what's like the next big thing? What's gonna be the thing that we all gonna be thinking about, talking about? You know, what's the thing that I need to learn to avoid being laid off the next time my company decides to go through layoffs, right? Because that's really what a lot of it boils down to, is we don't want to be made irrelevant. We don't want to be left behind. We don't want to, fill in the rest of these euphemisms. And one of the things that I've been watching over the last decade or so is, as developers, we wrestle with a tremendous amount of complexity. I mean, think about building your average web application and think about where we were, say, back in 1999 when you sat down, you wrote some HTML, you wrote some JavaScript, assuming people hadn't actually turned off JavaScript in the browser because it was considered a security hole back then. You remember those days? Right? There was this big fear that somehow JavaScript was going to lure people into typing in their passwords, et cetera, et cetera. We didn't have CSS, so we had to do all of our styling with tables. But fast forward a few years, and we had kind of figured out, oh yeah, no, what we really want to do, instead of doing this plain HTML 3.2 stuff, what we really want to do are Java applets, right? We want Java applets, or if you were a Microsoft fan, we wanted ActiveX controls running inside the browser. And that would be kind of that thick front end inside the browser that would be talking to something in the middle tier over Corba, perhaps, that would then go and talk to the database. And then we said, no, that's terrible. Let's not actually use this portable bytecode format thing inside the browser, because that would be a terrible idea. Let's actually do everything server-side rendered. So now this is where servlets and JSPs became really, really popular. And then we said, no, that's a terrible idea, because now we have to keep making all these long round trips back and forth between the browser and the server in order to do even the simplest of validation. Let's actually do a fair amount of JavaScript in the browser, right? As a matter of fact, let's get to that whole single page application thing, to the point where now we're actually talking about WebAssembly, which is a portable bytecode format that will run inside the browser because anyway, we've got one. And then, of course, now the big thing is, with all these single page applications, what are we trying to do with them? Render them on the server. You kind of feel like we're spinning in circles. 25 years later, the web application is still pretty much as complicated to build as it was when we first got started. Part of what we expect of a programming language is to elevate the abstraction level so that we as developers don't have to deal with as many of the physical details. This was the primary reason that C, for example, won out over assembly, in that it released a lot of the physical details that the assembly level developer would have to work from. This is part of what C++ did to win out over C, because now we could actually take state and behavior, combine them, and use them as a first-class concept. This is what let Java win out over C++. And of course, Java's kissing cousin, C#. Those two won out because they had a virtual machine, which would now allow us to forget a lot of these physical details. These allowed us as developers to kind of level up the abstraction levels that we work with. Well, part of what I think is going to happen is that we're going to see a new renaissance of programming languages emerge that will, in fact, eventually dethrone, more like absorb. Because remember, when object-oriented programming came around, it didn't completely replace procedural programming. It incorporated it. Instead of calling them procedures, now we call them methods. Instead of calling them global variables, now we call them singletons. That was a joke. The fact that none of you laughed at that joke says you're either very tired or taking this talk way too seriously. Right? I really believe that we are actually seeing some of this renaissance beginning to expand, but let me walk through some of why I think what I do. If we go back and look at some of the history of programming languages across time and space, programming language design has been, well, let me even back up further. Programming, period, has been broken up into two fundamental groups. There are the practitioners, the people who actually write code 40 hours a week. Usually it's code that they're paid to write. Usually it's code that they wouldn't write in their free time unless they were being paid. I mean, be honest, how many of you would actually work on the company's ERP system for free? There are no hands up. Come on, who doesn't want to? There's one person in the back who's like, yeah, me, I would do it. What's that? Your own companies, of course, of course. Yeah. Ever wonder, by the way, why there are so many different build tools in the world when most of the build tools do nothing more than what Make did for us like 40 years ago? It's primarily because programmers love writing code, but they hate working with users. And so they decide that they're going to work on something where they are the user. And that way they don't have to deal with idiot users. They can be the idiot. Wait, that came out wrong. But yeah, I mean, it's much easier to work on something when you don't have to interrogate and try to get the vision out of somebody else's head. It's your own head. On the other hand, there are the academics, the people who work in university and take students and teach them various things about programming. Question for you, how many people in this room would be genuinely excited, enthusiastic, in fact, about the idea of your new boss being a PhD professor from the University of Krakow? Couple of hands. How many of you would be really excited if that person was going to become your teammate? Couple of hands, maybe. How many of you would trust that they could actually be left alone on the project? And that's when all the hands come back down. Think about this for a second. In our industry, we really have a very dim view of the academic. We really don't think of them as being at the pinnacle of the field. If you go into the medical space, the people who are running hospitals, the people who are, in fact, some of the most valued members of the medical profession are all the people who have very impressive academic credentials. As a matter of fact, one of the best places to go work if you're a doctor is a teaching hospital, where they, in fact, do a tremendous amount of research and where, in fact, they have a number of basically interns who will follow doctors around, learning from them as they treat patients. If you're sick, you want to be treated at some of these places because this is where the best and the brightest in the medical profession are. And they're almost all of them involved in academia in some way. Over in our space, being a part of academia is almost a kiss of death. Academics historically are trying to figure out new ways to do stuff. They're trying to take some of the existing ideas and twist them around, or they're trying to create new ideas and shape them to be something that can actually work within the space of programming languages. They're, in some cases, trying really wacky ideas that may or may not actually fly, but their basic goal is to figure out how to create things, in many cases programming languages, that are going to make the development of software, or the maintenance of software, or the observance of software, the administration of software, et cetera, more effective, more efficient, quicker, et cetera, et cetera. Practitioners, on the other hand, are generally all about getting shit done. I need to make sure that when I am tasked with a story, that I can get that story done in the time that I've estimated for it to be done, which is to say I estimated X amount of time, and in fact it will take 2.5 X amount of time, because that's the general way that this works out. But I'm not interested in elegance, I'm not interested in purity, I'm interested in actually making sure the stuff gets done, because that's what I'm held accountable to by my management. And these two groups have historically been somewhat uninterested in working together. Actually, almost hostile. It's been an almost hostile relationship between practitioners and academics. And if you don't believe me, let me ask you this. When's the last time you sat down and read an academic paper on software development? There's like one person who's like, yeah. There's a couple of them out there. So where do our new ideas come from? Generally, we complain, those of us in the practitioner space, we complain that academics don't get it. Academics, when they start working with a new idea, they're often building something that really doesn't address some of the needs of the real world. If a professor comes up with a new programming language, that programming language often exemplifies that particularly new concept. But how does that language actually do some of the things that we needed to do, like, for example, access a relational database, or be able to access a document database, be something that could be easily deployed and run in the cloud, something that is able to expose an HTTP interface over the wire. Heck, forget HTTP, can I do any sort of networking capability whatsoever? And the academic historically has said, well, yeah, I mean, all of those things are nice, but that's not really what I'm trying to prove. I'm trying to prove this concept. So the practitioner who picks up this really nifty, brand new language that has these really interesting concepts discovers that, yeah, it's kind of interesting within its own world. But as soon as we start trying to plug it into the larger fabric of all the things that we need to do, it doesn't really go very far before we start running into all of these limitations. Because doing all of those things, getting all of those details correct, is hard. And it requires a degree of energy that a lot of academics, are not willing to put if it's not somehow reflective of the concept they're interested in proving. And in many cases, they don't have the bandwidth. They might have a graduate student or two working on the project, but other than that, it's just them. What that means is that these ideas, these new concepts, don't actually get explored. For example, how many people have heard of the Haskell programming language? Fair number of you, yeah. How many people had heard of Haskell 10 years ago? Couple of you. How many had heard of functional programming at all 20 years ago? Couple of hands. How many had heard of functional programming 10, 15 years ago, Haskell or any other language? Functional programming has been around for almost 40 years. It took that long for functional programming to actually make its way anywhere close to the mainstream, because it took that long for many of the functional languages that we work with to be able to do some of the things, such as, for example, access a relational database. Now, there's an argument that says, well, Haskell, Miranda, ML, these languages, they took time to bake and so forth. You're right, they absolutely did. And part of that baking time is people picking up the language, playing with it, seeing where it falls down, and then emailing the professor to say, hey, by the way, I couldn't do this with your particular language, and so it'd be nice if you could support that, or I found a bug, or et cetera, et cetera. C++ was first introduced really as C with classes back in the early 80s. Within the decade, it becomes one of the languages that's talked about very, very often when people start talking about object-oriented programming as we get to the late 80s, early 90s. By 1995, it's a mainstream programming language. That took 15 years. Java as a language was created somewhere in the early 90s. By 95, it became something of a mainstream language. So we can definitely see that some of these cycles are accelerating, but even so, if you're not working for a large technology company that has the opportunity to showcase a browser around your pet language at a large industry show like Comdex, where do you get that feedback? Where do you get that experience? Because that experience is absolutely critical to the feedback loop. The feedback loop is the most critical thing that we have figured out over the last 10 years. Everything agile is essentially about tightening up the feedback loop. The reason we write unit tests, to tighten up the time between when I write the code and when I see whether or not that code has a bug. The main reason we do 1 week, 2 week, 3 week sprints is so that at the end of each sprint, we show this to the customer and they give us feedback as to whether or not this is in fact what they were interested in building. Every single thing we do, the on-site customer, the whole 9 yards, everything we do is about tightening up that feedback loop. Well, if I'm developing a language and I want people to give me some feedback about how the language works and nobody's actually using my language, what do I do? There are a number of things in play, 4 forces in particular, that are actually making it easier to help fix this broken state of affairs that we've lived with for the longest time. Virtualization, language tools, a focus on linguistics and language concepts, and the notion of services and microservices. First off, virtualization. As a Java developer, you are freed from having to think about all these low-level physical details. You do not have to worry about allocating memory. You do not have to worry about releasing memory. For the most part, these objects just kind of come and go without any direct intervention on your part, unless you specifically want to get involved, aka you want to write a finalizer, or if you really, 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 really want to get involved, the JDK has had hooks where you could actually replace the garbage collector if you really wanted to. Nobody outside of Oracle has really wanted to for the longest time, but it's there, it's a possibility. If you want to deal with the physical details, you can, but other than that, you live in this nicely abstracted world where objects just kind of come and go. You also don't generally have to worry about what loading code looks like. Class loaders take care of that for you, and class loaders themselves are pluggable, and now we have modules and so on and so forth. And the JVM is certainly not alone. There's the Microsoft CLR, Ruby has a virtual machine, Python has a virtual machine. All of these VMs make it easier for us to think about and work with code because they elevate the abstraction level that we deal with. Those virtualizations help for language designers as well, because along with each of these VMs typically comes an ecosystem. And so if I'm getting ready to create a language, say, I don't know, I'm really interested in this concept known as aspects. I'm really interested in being able to do a limited subset of meta-object programming because I've spent a lot of time in the Lisp world and I see some of the advantages of doing that, but I also see some of the dangers. And I want to create a new language that explores this concept of aspect-oriented programming because my name is Craig Gonzalez and I really want to explore this space. Rather than doing all of the native code generation in my language myself, I have my compiler generate Java bytecode. And now, any aspect that I write has full access to the entire ecosystem of the JVM. And this is basically how Aspect-J came into play. If I'm really interested in figuring out how my ideas around the combination of an object-oriented language and a functional language should interact in a way such that we can get the benefits of both and avoid the drawbacks of both. If I do this on top of the CLR or the JVM, again, I get this whole ecosystem, so now we could actually start exploring what it would be like to take kind of a functional first approach to accessing a relational database. And I call my language F# if I'm Don Syme over in the Microsoft world, or I call my language Scala if I'm Martin Odersky and I'm over in the JVM world. If I really, really like Lisp and I want to explore those ideas, well, you get the idea. We call it Clojure, or there are actually several different Lisps that have been available for the JVM for quite some time. The language designer now can focus on the concept that they care about rather than focusing on the physical details. Tools are also important. Just as we actually make heavy use of IDEs and debuggers and all of that stuff, language designers want to be able to do the same. Being able to debug a language grammar is actually a really, really powerful thing when I'm trying to figure out what the grammar will look like. And we now have a number of those kinds of tools. Having tools that will be able to make it easier to optimize that code, whether I want to go to bytecode or to native code. GraalVM, Lena was just in here earlier talking about it. GraalVM actually taps into another interesting project called LLVM, the low-level virtual machine, which is, for all intents and purposes, a compiler toolchain. And LLVM is used in a number of the popular languages that are out today, most notably Rust. One of the reasons Rust got a lot of excitement is because Rust knows how to compile to WebAssembly. Guess how they got that functionality? Through LLVM. All of these tools make it easier for a language designer or the burgeoning language designer, the one who would like to be more of a language designer but doesn't know where to start. The tooling makes it much easier for it to be an approachable topic. On top of this, the fact that we have decided that collectively we just want to work through HTTP-based APIs or gRPC-based APIs means that now there's an encapsulation barrier. I don't really care how data is persisted, particularly because if you follow the microservices mantra, the way Amazon laid it out when they first started talking about microservices, there should be no shared dependencies. There shouldn't be a shared database. So that now you have free reign whether to store something in a relational database or whether you want to store it in a document database, or heck, if you want to store the whole thing in a giant Excel file, nobody will care because the only way to get at that data is to come through your service interface. This means now that I don't have to worry about my code being the same code that is running on the same platform that the next team over is using. So this offers up an opportunity for us to be more exploratory, even within a production environment. The earliest microservices companies, the companies that adopted microservices back in the early days, they very much opened up the waters to any language. And many of these microservices were written in Go, several were written in Java, many were written in .NET, Node.js. All of these languages suddenly had an opportunity to run in that space because, hey, what we're going to do is we're going to throw it all into a Docker container and throw that up in the cloud anyway. And the Docker container is going to isolate from anything else, so yeah, who cares what language you use? If you really wanted to write your microservice in COBOL, go for it. But the other thing that's happened recently is we've actually started thinking about languages in a way that we really hadn't. Throughout the 2000 and 2010 timeframe, there was kind of this idea that objects were really the only thing we ever needed. That in fact, everything we wanted to do could be expressed as an object. And this was part of the reason why we had so much pain when we got to some of these transactional systems like EJB. Because EJB, with its notion of stateless and stateful session beans and enterprise beans and so forth, frankly, it actually invalidated a good number of the things that we really expected objects to do. The whole notion of an entity being essentially just data and session beans being just logic, well, I mean, it makes sense to some degree from a services perspective, but from an object perspective where, again, remember, we're trying to combine objects and data into a single entity, it just made no sense. But what we've started to realize is that, well, yeah, that functional transactional approach is actually a very, very useful one. Not everything can be wrapped up into an object. As a matter of fact, there's a lot of interesting ideas, and functional languages were really the ones that kind of broke this idea into play, such that we started going back and thinking about what each of these languages brought to the fore. Procedural languages over assembly language gave us a certain amount of structure, and object languages allowed us to combine data and behavior into a single first-class entity. And functional languages brought us type inference and pure functions and so on and so forth. As a matter of fact, Paul Graham on his blog cites that there are 9 ideas that Lisp popularized. And of course, in his worldview, these are the only 9 ideas that matter because Graham is an unavowed Lisp bigot. And he will actually talk about how every so often a language designer will pick one of these ideas off the list, trot it around for a while, and then release it in their language as if, oh my gosh, it's completely new, it's completely beyond amazing. And all they're doing is basically recycling ideas from Lisp. And there are a number of ideas that the Lisp language, which again, remember, was designed, let's see, that was a 1960s era language. And these ideas have been around, it's just we had a hard time figuring out how they would fit into some of our mainstream languages. But for example, notation for code using trees of symbols and constants, the AST, Microsoft actually exercises this as a part of their LINQ library, LINQ. That's how they actually do the transformation of your C# code into actual SQL statements that will execute against the server. Now, is this the only list? No, there's tons of ideas. And frankly, the academic community is exploring a number of new ideas. But let's stop for a moment and talk about some of these ideas here for a second. This is Haskell, for those of you who have never seen it before. It's a functional only. There's no concept of an object anywhere in Haskell. The notion there is we are binding a value. In this case, we're binding a list of numbers to the named numbers. So this is essentially the allocation of a list that we can now manipulate. The curly bracket hyphen, by the way, that's how they do comments in Haskell. And so that's basically showing us what would be printed each time we do one of these things. Notice that head of list, well, we're doing something with that numbers list from the previous slide. In this particular case, we're using a function called head, which says, let me remove the first element in the list. Notice that this is somewhat procedural in its notion in that we call the function and pass the value as opposed to invoking the method as if it were on the list itself. Functional programming really wants to tear apart the idea of state and behavior, or rather functions and data, because then functions can actually operate across a variety of different sorts of data, whether this is an array of numbers or an array of strings or an array of anything. Implicitly, we are seeing generic behavior here without any of those sharp, pointy angle brackets poking our eyes out. So here, head of list is going to be the head of the numbers list, which would be the integer 1. And last gives me the last element in the list. Tail will give me everything other than head. And take says, let me take the first n number of elements off of that list and return it as a list. Okay, pretty straightforward stuff. But again, we're basically calling functions on data. Now, Haskell also has this idea of a range. See, the idea of a list, the idea of a range, all of these are essentially sequences in Haskell terminology. So here, rather than having to explicitly type out 1, 2, 3, 4, 5, etc., we can use this range operator to say, I want everything between this value on the left and this value on the right inclusive. And then, if I can discover the pattern here, in this case 2, 4, okay, the pattern presumably is we're adding 2 each time. Great, well 2, 4, 6, 8, 10, 12, etc. This range concept, by the way, has made its way into a number of our mainstream languages. If you do anything with Kotlin, if you do anything with Swift, they have this range object. The key thing to understand here is that this is not actually a list. That is to say, we don't actually have all 100 of those numbers instantiated in memory when we first create number range. What Haskell will actually do is create an object that knows how to produce the next number when requested. Now, there's other ways to, in fact, be able to create a list out of code, a little bit more explicitly. So here, what we see is a comprehension at the very top line there. What we're saying to the left of that vertical pipe there is that x, for each x, we're going to assign x a value from the range 1 to 10. And then after we've evaluated each one of those elements in that range, we will return it, which basically gives us a list of 1 to 10 values. If this is starting to sound a little familiar, by the way, it's because Brian Getz and the rest of the folks at Oracle stole a lot of these ideas as part of the Java 8 stream library from Haskell. If you've spent any time with Python, or if you've spent any time with JavaScript generators, this is the same idea. The last chunk there is basically the FizzBuzz problem, where essentially we test each number from 1 to 25. If it's divisible by 3, print fizz. If it's divisible by 5, print buzz. If it's divisible by both, print FizzBuzz. Classic programming problem for an interview. And this is how I produce that list of results as basically a list of strings. This is a little bit more filtering and transformative, but again, it's all about functions applying to particular data elements. Haskell will also allow us to create an infinite list, or to be more accurate about it, an infinite stream. And this is kind of an odd idea. Why would I ever want to have a list of infinite numbers? I mean, because if I try to print it, it will literally never terminate. The program will keep printing until basically we start running out of space on the CPU. Because no matter how big the CPU, we can't capture infinity, and we certainly can't hold all of these in memory at the same time. But Haskell still has this concept because it turns out to be useful in certain scenarios, where I can take the first couple of elements from the stream, or I can actually cycle through a stream infinitely, et cetera, et cetera. Now again, this infinite list thing is kind of strange, odd, silly, et cetera. But if you think about what Haskell is doing here, if you think about that range object, what we're basically talking about is a Java iterator that doesn't actually operate off of a collection. Because remember, the iterator object is always paired with a collection object because the collection is the source and the iterator knows how to get the next value from the source. But if the iterator knows how to manufacture that next value, we don't actually have to have the source. The iterator can just kind of walk us through. So here, for example, this is a Java class that masquerades as an iterator. Well, it really is an iterator. It implements the correct interface. And notice that when we return this iterator of integer, it has all the necessary iterator methods on it. Can I keep going? That's what the hasNext method tests. And what is the next value? But rather than getting it out of a list, it manufactures it so that at any given moment in time, this iterator will only ever occupy basically one integer's worth of memory to tell us what the next value that we're going to produce will be. Okay, I suppose if you really want even numbers that badly, such that you could loop through them in a for loop, yeah, I guess you could do this. But remember, the iterator just knows how to create the next value. And it means that that creation could, in fact, come from a variety of different places, including a file. So all that code you write in order to be able to loop through a file can actually be reduced if we have an iterator that knows how to loop through the lines in a file by using the file as the source, and the iterator keeps giving us strings back. So same basic idea here. We open readers, and then we create the iterator around the buffered reader, and each time we go through, we grab the next line and have it ready to hand back. That way, hasNext can return false if, in fact, we've run out of lines. Such that now, iterating through a text file is just a for loop. The nice thing is, this will only ever occupy one line's worth of memory rather than slurping the entire file into a buffer and then walking through it line by line. For a 100-line CSV, this isn't a big deal. If it's a 10 million line CSV, that could very much make the difference between success and an out-of-memory error. What this line of thinking did is it took us down a really interesting path that said that iterables and iterators are actually vastly more interesting than we ever realized. That in fact, they are interesting constructs in their own right, because if they know how to manufacture that next value, then I don't really need the collection as a whole. And a lot of this thinking was what guided the design of the Java Streams library. That's why it was also abstracted out to be producers and consumers, things which know how to produce the next value versus things which are designed to consume values that are coming from a producer. But let's go back to the infinite stream concept for just a second. Because at least, when I first ran across this, I could not for the life of me figure out where in the world there is ever an infinite stream. Why would Haskell even bother with this concept? Because it doesn't ever occur in reality. Except it does, to some degree. If you think about data coming over a socket, if you think about data coming over a serial port, if you think about the mouse movement and mouse clicks and key presses and all of that stuff, when you build a graphical user interface application, whether it's a mobile app or even whether it's a web app, somewhere buried deep down there is a spinning loop that is gathering data from the hardware and exposing it as events to be consumed. It is literally an infinite stream. And so then, if we write functions that know how to pull the head off of that range, off of that sequence, off of that stream, well, if we're comfortable with working with infinite lists, then the whole notion of this data, these collection of events coming from some external source, it's just another infinite list. And if we in turn make our responses to that a function that says, oh, okay, so now we've gotten a mouse down and it happens to be in this space. Okay, so I've got a function attached to that particular area of the screen, which in turn says, now it's time to do some particular calculation, et cetera, et cetera. We've now walked very clearly into the realm of user interface programming, which takes us directly to the space known as reactive programming. And it was these principles on which the React library was built. And it was these principles which in turn have led us to functional reactive programming and some of the various user interface libraries such as Swift UI, Jetpack Compose, et cetera, et cetera. All this because somebody sat down, looked at Haskell and said, I wonder why they do it that way. Now, there's definitely no shortage of problems that we as developers have to deal with. I mean, frankly, you just start taking a look at some of the tools that we've got. Don't get me wrong, I love Josh Long, I love Spring Boot, but the amount of code that it generates when you create a brand new project is frightening. It is frightening to me. Hello World is supposed to be 4 lines long. And when you do a Hello World Spring Boot app, in order to be able to have a Hello World API service, the amount of stuff that gets generated there that I as a developer am now responsible for is just off the hook. We have to deal with this notion of concurrency. Some of you may not be old enough to remember, but back in the 2010 timeframe era, Herb Sutter wrote an article that said the end of the free lunch. The era of the free lunch is over. And what he was referring to was the fact that thanks to Moore's law, which says that basically Moore's law says that we double the number of transistors per square inch on any given piece of silicon, which we have internalized to say, okay, every 18 months, CPU speeds will double, memory availability will double, hard drive sizes will double, and this has remained astoundingly consistent across the last 45 years, except for CPU speeds starting in about 2010. Because all of a sudden, instead of doubling the CPU speeds that we were used to, which, by the way, was a really, really cool thing, because if your boss came to you and said, hey, the program's running too slow, you would say, all right, boss, we'll take that as the next project. We will do performance improvements across the board, and we will aim for a 2x speed improvement, and the project will take, I don't know, about 18 months or so. And then you go back to your cube, because your boss now has walked away, because this is long before the era of Agile. Your boss walks away, and you play Quake for the next year and a half, and then tell them, hey, we actually have a build, we just need to buy new hardware, and lo and behold, it runs twice as fast. And you're brilliant. Yeah, we can't do that anymore, because CPU speed stopped climbing. What we did get, though, was we got more of them. So now all of a sudden we're living in this multi-core world. And of course, NVIDIA is riding this horse like you wouldn't believe, because all those graphic processing units, I mean, your modern graphics card has 32, 64, 128 of them, ridiculous number of these chips. And programming languages are struggling to figure out how we actually tap into that, because programming to that degree of parallelism is something that most of our languages today do not do well. There's also some of the drawbacks that come with a pure object model. If you were to actually program in a pure object-oriented language, you would actually embrace something like Smalltalk, where everything is an object. JavaScript actually comes pretty close with its prototypical inheritance style, where everything is an object, including the thing that was used as the template for the object that you're currently in. But even that has significant drawbacks, because when all I want to do is take a couple of objects and perform some operations on both of them. Here is a person object, here is a person object, now I want them to get married. Fowler calls this the transaction script in his Patterns of Enterprise Application Architecture. Where do I put that transaction script? Because if you're Java and you're a pure object-oriented language, the only thing we could really do is create a static method on a class, or we make it a strategy, which is basically a method that is surrounded loosely by an object. Or now we could actually use a lambda, which is basically a method surrounded by an object. It's just the compiler does that for you. It doesn't really fit within a traditional object-oriented model. So where exactly does some of those just step-by-step transactional instructions, and by the way, transactions themselves, transactions are an amazing thing. Those of you who have spent any time working in a SQL database, playing around with it, experimenting with it, trying to query and access and update data with it, you gotta love the transaction, because you can go in, begin transaction, and then you can do whatever the hell you want to the database. You can even drop the database if you so desire. All it takes is a single rollback, and it's as if it never happened. Personally, I want to live a transactional lifestyle. You go into the store and you buy that t-shirt that makes you feel like you're 30 years younger, and it just looks terrible on you. You're like, rollback. And you never bought it. You walk into the nightclub and you see the cute girl over there and you say, ha, completely botch your opening. Rollback. You've been married for 20 years and you decide it's done. Rollback. Wouldn't that be awesome? Think about how much of our code, by the way, would be made easier if we had transactions at an object level, where I would actually say, okay, I'm going to update these 4 objects with new state information, and if for whatever reason any one of those updates fails because perhaps it violates a business rule to do so, then all of them revert back to their original state. In-memory transactions is one of those things that we've been chasing in the language space for quite a while, particularly because it would naturally flow into database transactions very smoothly. Don't get me started on the security story. Don't get me started on the distribution story. Lastly, let's talk about UI here for a second. Who here is really happy at the amount of work it takes to create a user interface on the web or on a mobile device compared to, I don't know, doing something as a command line tool? I actually had a development team at one point that wanted to deliver a custom business app to the users as a command line app because it was so much easier. And they said, no, we'll just train the users to understand it. They're not stupid. They'll figure it out. This graphical stuff is, and the industry is responding. We're actually seeing a crop of new languages that are emerging that are trying to address some of these issues. For example, go back to the Spring Boot example, and I want to create a Hello World service, which should ideally be 4 lines of code, but at the very minimum, be 1 page. Hello, Jolie. Jolie is a programming language that is a service-oriented programming language, not object-oriented. Objects will factor into this, but specifically looking to create services as a first-class construct within the language. Brings a structured linguistic approach to the programming of services, including constructs for access endpoints, synchronous and asynchronous operations, etc. This is Hello Jolie. This will produce a fully HTTP-enabled JSON endpoint running on port, let's see, it's right there in the code, on port 9000, because notice the location is specified, and notice that it's being done as a socket, and we're doing this over HTTP using JSON as the data format. It's all right there in the code, and it's compiler verified. If you have ever had a service fail on you because you got YAML wrong, because there is no compiler check for YAML, or JSON configuration files for that matter. By the way, Jolie actually runs on top of the JVM. So Java is its foreign function interface, so it has full access to everything else in the Java ecosystem. But speaking of deployment and whatnot, putting stuff up into the cloud, how many of you have found it difficult to unit test stuff that gets deployed to the cloud? Well, even if it's not difficult, it's expensive, right? Because if you're going to test stuff, you really should test it in an environment that's identical to the production environment, which means that you're going to need to stand up a cloud environment twice. One purely for your testing scenarios and one for your actual production scenario. Hello, Wing. Wing is a cloud language, and as a matter of fact, when you write this code, there is a Wing desktop that runs on your machine that mimics what AWS would look like. So here I am instantiating, if I deploy it to AWS, because there's nothing AWS specific about any of this, it could easily be in Azure, it could easily be in GCP. I'm creating a queue, I'm creating a bucket, and every time somebody sends a message over that queue, we modify a file stored in that bucket. And this is, 10 lines of code. What's more, when you wing it, like literally that's the command line, wing it, it will fire up a replication of the cloud on your local machine with all these mocks for the buckets and the queues and so forth, such that you can test with a fairly high degree of certainty, because again, the whole point of the compiler is to hide a lot of these physical details away from you. And when you decide to compile and go to production, Wing will transpile into a Terraform script, which then means you're fully into infrastructure as a service or code as infrastructure or whatever the hell acronym we're using these days. It's now code that describes your cloud deployment. Now, a lot of people are very, very excited about the idea of how AI could be used, natural language as inputs and so forth. Well, I'm here to tell you that we didn't need AI to do this. We, in fact, had a programming language called Inform, which was used for interactive fiction. If you ever played any of the adventure games like Zork or any of the Lucasfilm games, I'm trying to remember the one pirate one, and there was yeah, you guys remember which ones? Yeah, those are all interactive fiction games, and Inform is a programming language specifically for creating those sorts of games, and this is what code in Inform looks like. Now, this is legit programming language here. You'll notice that it's obviously white space sensitive. The indentations are important. And there is that verb there, say. That's obviously how we're going to do output. But a good number of game engines actually operated off of code that looked very, very similar to this. And this is actually something that you can put in front of somebody who's entirely 100% not a programmer, and they have a very, very strong chance of getting it right. By the way, Inform itself is written in a style called literate programming, where in fact the documentation is actual descriptions, and it can be hosted. And here, actually, let me do this real quick, because this is just too fun to show off. This is source code. Don't believe me? Let's look at the contents page of the core module. This is source code. The source code and the documentation are deeply intermixed. And then tools will come through and, well, on the one hand, we want to compile it into an executable. We focus on the code parts of the file. We also want to generate the documentation, so we focus on the documentation parts of the file. And they are always kept in sync because they are literally the same file. That's kind of fun. And the language tools that are available to us are all over the place. We've got Antler, which is a parser generator. We've got several of these different packages that know how to generate JVM or analyze or annotate or change JVM, CLR, Python, whatever your particular virtual machine of choice is. We can muck with their bytecode. I already mentioned LLVM. If you sit down and spend a little time studying how to write a grammar file, for example, you can build your own toy language from zero to I now have a working interpreter in about a week. This is not the province of PhDs anymore. Or maybe you take an existing language and tweak it. So for example, this is what's known as an internal DSL in Scala. All of this is 100% Scala code. The Scala compiler will compile it as long as you have a particular library on the path, which, you know, as relational access syntax goes, that's pretty close to SQL. Or perhaps you spend a lot of time working with XML and you really want to do so from a scripting language like, say, JavaScript. This was an actual ECMA standard. It was called E for X, ECMAScript for XML, and it was incorporated, it was implemented in the Rhino JavaScript engine, which Sun owned for a long time, and then Oracle basically gave over to JetBrains. But here you can see that we are actually instantiating an XML literal to that and assigning it to that order object. And then order.customer.firstname is navigating through the XML tree. Nothing stops us from doing this today in JavaScript other than the fact that nobody seems to care. Now, fair question to ask, how real is all of this shit? Because a lot of these languages don't seem to go very far. As a matter of fact, most languages have a use curve that looks something like this. The person who created them uses them for a couple of years, gets bored, and moves on. The worst scenario is the person who created the language convinces a couple of their best friends to start using the language, and then it gets adopted at a company, and now that company is stuck with it for the next decade or so. But there are some languages that cross the threshold of immortality. And yes, COBOL, I'm looking at you. Seriously, COBOL will never die. COBOL will never, ever, ever, ever die. Because even though COBOL is a 70-year-old programming language, it still cashes your paycheck on a regular basis. And the cost of replacing it is just way too high, because the chance of a bug appearing in there that isn't actually already there and that everybody's worked around, yeah, forget it. You're never going to replace COBOL. If you are looking for a programming language that will guarantee you employment for the rest of your career, learn COBOL. It's not. What's that? AI will rewrite the COBOL. Is that what you're saying? Get out. Get out. There are some real reasons, there are some real concerns here, right? If I've convinced you that one of these languages is interesting and worth pursuing, or the idea that you're going to actually sit down and start to work on your own DSL for the company in order to make the company able to be more nimble and responsive, there's all these blockers, right? My boss won't let me use it. My team won't let me use it. The inherent fear of what if I'm wrong with this approach? Okay, the boss. Yeah, okay, some bosses are just idiots. And sometimes you go above them to say, hey, let me go talk to the boss's boss and see if I can convince the VP or the CTO that this is a worthwhile thing to chase. Sometimes we work around them. What the boss doesn't know can't hurt them, right? I didn't say that out loud, by the way. I will vehemently deny it. As a matter of fact, I'm deleting this video as soon as I get my hands on it. But in some cases, in most cases, bosses are actually genuinely interested in things that can be shown to have a net positive effect on what we're doing. So then it becomes up to you to prove that utility. Show them that it can be useful. Back in the days when Groovy was new, one of the things we used to tell people is, look, you've got to write all these tests, but the tests aren't going into production. Write the tests in Groovy. Because as a dynamic language that understands the statically typed JVM, it actually makes it fairly easy to write tests in, but your core code remains in Java. And when the boss comes and starts looking at the Groovy code, it looks enough like Java that when the boss says, hey, what is this? You just tell them, oh yeah, this is the next generation of Java. They added a few new keywords. It's very technical, boss. You should just go back and write more emails. I say that as an engineering manager, by the way. My team won't let me. My team doesn't trust this idea. Well, part of this is looking at the team's concerns, right? Because if you're a junior developer, part of what your concern is, will I be productive in this? I'm getting my career off the ground. I just want to be able to do stuff. They're actually going to be the most flexible. The senior developers, the ones who have spent the last 10, 15 years perfecting their understanding of Java, now all of a sudden you're throwing them a new language their way where they will be learning at the same time the juniors are. That's where you're actually going to get a fair amount of pushback because, well, now I'm not an expert in this thing anymore. Oh, I don't trust this. Again, part of this is demonstrating the utility, giving them some examples, giving them a mental model to work from, and incorporating them into the definition of the language. Let them factor in how this is going to work. But what if you're wrong? What if you put all this time and energy into building this thing and all of a sudden it turns out to be the wrong choice? Well, yeah. What if you chose the wrong framework? What if you made the wrong decision with respect to the CI/CD tool? Or what if you made the wrong decision with respect to how we were going to do our unit tests? It's the same basic story. And in fact, giving a language to people can actually be a lower learning curve than giving them a framework. But you as the initiator of this story, you as the champion of this story, you have to do your homework first. You have to make sure that you are in fact solving a problem that other people actually have. And if you do that, and if you're ready to be wrong about certain parts of it, somebody says, well, we really don't need this part of what you're working on. Okay, cool. Set that to the side and work on other parts to be able to get them that value quickly. Most people will come along with you on this particular journey. Because frankly, nothing ventured, nothing gained. Faint heart never won fair lady. High risk, high reward. There's all kinds of phrases we have for basically, yeah, if you want to actually accomplish something, you're going to have to face that fear of being wrong and stare it down. They're everywhere. Languages, programming languages, these new ideas, they're everywhere. Keep an eye out. Look not only at some of these new languages that are emerging, but also look at some of the old ones. Much of how JavaScript's prototypical-based inheritance works was not something that they came up with from scratch. A lot of it was actually leveraged from an earlier programming language called Self. That whole notion of an object is just a bag of name-value pairs where the values can either be data or objects. And we have a runtime relationship to our quote-unquote parent object. All of that was something that Self had figured out 15 years before JavaScript was even a twinkle in Brendan Eich's eye. Languages like Smalltalk, which do message-based dispatch, dynamically typed, all of these different things. Again, Lisp, I mentioned that earlier. All of these different languages, their decisions ripple down through history. And so, for example, there is still a fair number of scientific computing that is still done using Fortran. Here's a homework assignment for you. Why? What made Fortran such a popular language for doing all of this mathematical work? And is there, in fact, a way to bring some of those concepts forward into a language so that if you work at an oil or gas company where a lot of that stuff happens, you now have the ability to allow those folks to take their subject matter expertise and express it in a language that they're familiar with, using concepts they're familiar with, that are running on top of a modern platform. Something we sometimes forget. Tools were meant to serve humans, not the other way around. So should it be with programming languages. Peace out.